Dear students, after studying this module, you shall be able to know about the three famous named reactions, that is von Richter reaction, Sommelet-Hauser reaction and Smlies rearrangement. Learn the various types of rearrangements, identify these named reactions by just the reaction given, and understand their reaction mechanisms also. Now students, these three reaction mechanisms or the three rearrangements, so to say, that is the von Richter, Sommelet-Hauser and Smlies rearrangement, are very famous type of rearrangements or reactions, and we will begin with the introduction of von Richter reaction. The reaction of aromatic nitro compounds with potassium cyanide to generate a carboxylic acid at the ortho position to the nitro group is known as Victor von Richter reaction. That is, it was discovered in 1871, and notice that generally the groups entering when already the group present is nitro goes at the meta position, but here in this von Richter reaction or rearrangement, here it is going to the ortho position. When aromatic nitro compounds are treated with cyanide ion, the nitro group is displaced and a carboxylic group enters with sign substitution, always ortho to the displaced group, never meta or at the para position. The von Richter reaction can be inhibited by the presence of potassium ferricyanide, and its molecular formula is K3FeCN6, and also sodium sulfite. Now brief display of the reaction is given here. Notice the nitrobenzene and the attack by the cyanide ion, which gives rise to the benzoic acid, and the next one. As with other nucleophilic aromatic substitutions, the reaction gives best results when electron withdrawing groups are present in the ortho and para positions, but yields are low, usually less than 20% and never greater than 50%. The reaction has a limited application in organic synthesis. The mechanism of von Richter reaction or rearrangement, let us study it in detail. The reaction proceeds via nucleophilic attack of cyanide ion ortho to the nitro group, followed by an intramolecular rearrangement, as you can see. Now see the attack of the cyanide ion primarily at the ortho position to the present nitro group on nitrobenzene, substituted at the para position with a Z group, which is preferably an electron withdrawing group. Now you can see by a series of intramolecular rearrangements, you finally arrive, the substitution is at the ortho position to the initial nitro group, that is the substitution is of the carboxylic group ortho to the nitro group present. The nitro group leaves and the incoming COOH group, that is the carboxylic acid group, it is at the ortho to the initially present nitro group, and the Z, which is the electron withdrawing group, remains intact. Now it is meta to the carboxylic acid group, which has been positioned there. First, the cyanide ion attacks the carbon atom in ortho position to the nitro group, as explained by me. After this, the compound regains its aromaticity once again. Now you can see that this step is important. In the next step, the negatively charged oxygen atom attacks the neighboring carbon atom and a 5-membered ring is built up. It opens under building a carboxylic acid group. Next, another 5-membered ring is formed. After a condensation reaction resembling Michael reaction, a double bond is built between the two nitrogen atoms which are present. Elemental nitrogen is then cut off from the opening of the ring. In the last step, students, you can see that the compound is protonated and the 3-halogen benzoic acid is finally formed. Now I hope you have understood the Victor von Richter reaction, in which there is an intramolecular rearrangement leading to the incoming group ortho to the leaving group, that is a nitro group. Let us now discuss in detail about the Sommelet-Hauser rearrangement, next in the series of these named reactions or rearrangements. The rearrangement reaction of certain benzyl quaternary ammonium salts in presence of sodium amide or another alkali metal amide to form N-dialkyl benzyl amine with a new alkyl group in the aromatic ortho position is known as the Sommelet-Hauser rearrangement. The Sommelet-Hauser reaction is highly favored in polar solvents like ammonia, DMSO, that is dimethyl sulfoxide, and HMPA, hexamethyl phosphoric acid. Low temperature conditions, they also favor this particular Sommelet-Hauser reaction. Now briefly, if you see the reaction here, it is shown, that is the reaction of benzyl quaternary ammonium salts in the presence of sodium amide or another alkali metal amide, and it gives rise to the N-dialkyl benzyl amine with a new alkyl group, as you can see, which is at the ortho position, is formed. The product formed, that is the benzylic tertiary amine, can further undergo alkylation and the product is again subjected to this rearrangement. This process continues until the ortho position is blocked. That is, all the ortho positions which are available are blocked. This rearrangement reaction has high yields. It occurs with various types of groups present in the ring. Now, if you compare this reaction, students, with the Victor von Richter reaction that we studied just now, you can see here that the yield is very high as compared to that von Richter reaction, in which the yield is always less than 50%. Sommelet-Hauser reaction occurs with different types of group present in the ring. The Stevens rearrangement, another reaction, is a competing reaction to the Sommelet-Hauser rearrangement. Let us now study the mechanism of Sommelet-Hauser rearrangement. The reaction proceeds via deprotonation of the benzylic methylene protons, which is acidic to yield the benzylic halide. The halide formed is in equilibrium with the second halide that is formed by deprotonation of one of the ammonium methyl groups. The second halide, which is present in much smaller amounts, undergoes a 2,3 sigmatropic rearrangement and subsequent aromatization to form the final product. Now you can see this mechanism clearly over here, how this rearrangement is taking place and how the 2,3 sigmatropic rearrangement finally gives rise to the aromatization of the final product. Now students, comes the last, that is the Smlies rearrangement. In 1894, R. Henrique reported that the base treatment of bis 2-hydroxy 1-naphthyl sulfide afforded an isomeric compound, that is 2-hydroxy 2-mercapto bis 1-naphthyl ether. 2 decades later, O. Hinsberg, as you remember from the Hinsberg test of amines, carried out a similar set of experiments with the corresponding sulfones, but it was actually S. Smlies and his co-workers who established the structure of the products. Smlies recognized that these set of transformations belong to separate set of intramolecular nucleophilic rearrangements. Hence, the name of the rearrangement got to be Smlies rearrangement. The Smlies rearrangement, students, is an example of intramolecular nucleophilic substitution. Remember, it is intramolecular nucleophilic substitution. It involves attacking on an aromatic system bearing an activating electron withdrawing group at ortho and para positions to the reaction center connected to a heteroatom. Smlies rearrangement is further accompanied by the migration of an aromatic ring from the heteroatom binding to the reaction center to a more nucleophilic heteroatom. Now students, this you can clearly see in this reaction that this carbon is attached to another heteroatom. That is how this rearrangement takes place. Here X can be a sulfone, a sulfide, an ether or any substituent which can dislodge from the arene with a negative charge. The terminal functional group in the chain end, that is Y, acts as a strong nucleophile, for example an alcohol, amine or thiol. In the Smlies rearrangement students, the nucleophile Y is generally the conjugate base of SH, that is the thiol, SO2NHR, SO2NH2, NH2, NHR, hydroxyl or OR. Now you can see here the reaction, and we have told specifically what is X and what is Y in this reaction system. In the presence of base, the Smlies rearrangement finally takes place. It has been observed students that a moderate electron withdrawing group, preferably in the aromatic ortho position such as chloro and alkoxide, can accelerate this Smlies rearrangement. On the contrary, the steric hindrance arising from a substituent at a particular position in the aromatic ring may facilitate this rearrangement. The solvent such as THF has been found to give positive effect and increase the rate of Smlies rearrangement. This reaction has been extensively modified by the use of different ethers as well as various reaction conditions. Now let us shift our focus to the mechanism behind the Smlies rearrangement. Now in this example, where you can see the X directly attached to the ortho position, ortho to the Z, X is equal to oxygen and Y being a heteroatom is the nitrogen atom. The end group amine after loss of proton acts as a nucleophile and attacks the ring carbon, followed by detachment of the ether oxygen from the ring. Now notice student, in the mechanism of Smlies rearrangement, how the ethoxide ion is actually taking out the proton and making the end group amine act as a nucleophile, which further attacks the carbon which is attached to the oxygen, that is the ring carbon which is directly attached to the oxygen as a heteroatom. Then it is followed by the detachment of the ether oxygen from the ring. Notice how after the attack of nitrogen or the end amine as the nucleophile, how the oxygen gets lost from the system, that is the attack of the nucleophile makes the oxygen leave from the ring carbon atom, giving rise to the final product. Now students, true Smlies rearrangement is a modification of the Smlies rearrangement that we just now studied. Let us talk about it in some detail. The true Smlies rearrangement is an extension of the Smlies rearrangement, and this rearrangement stands for the migration of an aryl group of diaryl sulfones when treated with a strong base, such as the rearrangement of mesetyl paratolulyl sulfone to 2,4-methylbenzyl 4,6-dimethyl-benzene sulfonic acid and the rearrangement of phenyl paratolulyl sulfone to orthobenzyl benzene sulfonic acid. This rearrangement is generally carried out under two distinct conditions. First is the metallation of diaryl sulfones by butyl lithium in ether and by potassium butoxide in DMSO. These are the two conditions, and under both conditions the three isomers of mesetyl tolulyl sulfones give three different products with retention of toluene orientations in the products. Furthermore, students, mesetyl beta-naphthyl sulfone gives only 5% of rearrangement product under N-butyl lithium ether conditions. In the modification called the true Smlies rearrangement, the incoming nucleophile is sufficiently strong that the arene does not require additional activation. The prototypical true Smlies rearrangement requires use of a strong base such as organolithiums, just as we discussed butyl lithium, or potassium butoxide to form the benzylic carbanion that undergoes the rearrangement. Now you can see here how the bully, that is the butyl lithium, is acting as a strong base over here, and it forms the benzylic carbanion that further undergoes the rearrangement to give you the product. Several other aromatic sulfones undergo a similar rearrangement. The rearrangement of aryl sulfones has been extended to aryl alkyl sulfones also. This rearrangement has certain applications in the preparation of aromatic sulfonic acids. The reaction rate is greatly enhanced by the substitution in the 6th position, that is the methyl chloro and bromo group of the attacking ring for steric reasons. The enhanced rate comes about because the most favorable conformation the molecule can adopt to suit the bulk of the 6th substituent is also the conformation required for the rearrangement. Thus, less entropy of activation is required for completion of the reaction. Now, let us talk of the mechanism of the modified Smlies rearrangement or the true Smlies rearrangement. When sulfones is treated with butyl lithium, deprotonation led to the formation of benzylic lithium compound. True Smlies rearrangement and hydrolysis of this intermediate gives the sulfonic acid. Now you can see here how exactly when the sulfone is treated with butyl lithium, how deprotonation is taking place and the formation of benzylic lithium compound, finally leading to the product formation. One example of true Smlies rearrangement is shown. Here you can see the modified or the rearranged product in the product by the strong base as the hydroxide ion in this case. Now students, let us summarize this module. In this module students, we have taught you 3 main reaction systems. First is the von Richter rearrangement, second is SommeletHauser rearrangement, third one is the Smlies rearrangement, and a modification of the same is the true Smlies rearrangement. First, we studied the von Richter rearrangement, that is in which the reaction of aromatic nitro compounds with potassium cyanide to generate a carboxylic acid ortho to the nitro group is known as von Richter reaction. Now as you know, in this reaction the nitro group basically leaves and the incoming group is ortho to the nitro which is present. Generally, nitro groups are meta-directing, but here only the ortho product is formed, never a para product is formed. The rearrangement reaction of certain benzyl quaternary ammonium salts in presence of sodium amide or another alkali metal amide to form N-dialkyl benzyl amine with new alkyl group in the aromatic ortho position is known as the Sommelet-Hauser rearrangement. The Sommelet-Hauser reaction is highly favored in polar solvents like ammonia, DMSO, HMPA. Low temperature conditions also favor the Sommelet-Hauser reaction. Also students, you have to remember that the yield of Sommelet-Hauser is much more than the yield which is obtained in von Richter reaction. The Smlies rearrangement, then next we taught you. It is an example of intramolecular nucleophilic substitution. It involves attacking on an aromatic system bearing an activating electron withdrawing group at ortho or para position to the reaction center connected to a hetero atom. Now we talk of the different Smlies rearrangement, that is a modified Smlies rearrangement, which is known as the true Smlies rearrangement. It is an extension of the Smlies rearrangement, and this rearrangement stands for the migration of an aryl group of diaryl sulfones when treated with a strong base, and such as a rearrangement of mesetyl paratolulyl sulfone to 2,4-methyl benzyl 4,6-dimethyl benzene sulfonic acid, and the rearrangement of phenyl paratolulyl sulfone to orthobenzyl benzene sulfonic acid. Now students, here I would like to state an important point, that these few reactions, when they are given without the name, can be very confusing. But once if you understand the mechanism of von Richter, the Sommelet-Hauser, Smlies and the modified Smlies, that is a true Smlies rearrangement, you can never fall wrong with the decision of the product that has to be made. Thus, this module serves an important informative lesson for these very important named rearrangement reactions in organic chemistry.